So we have learned from the previous video about fields, electric fields, and we know that if the lines are close together, that means the field is strong. If they are far apart, means the field is weak. So it is possible to measure the strength of the electric field, and to measure the strength of the electric field, we have this quantity called electric field strength. So the definition of electric field strength is just this: force per unit positive charge. So I explained to you how we get this formula. Now what it means is, to find how strong a field is, example, let's say you have a lithium ion. So usually a nucleus of lithium will be positively charged because it's just the nucleus, there's no electron. So let's say it's positively charged. Do you agree there will be field lines all outwards? Correct, not radially outwards, right? Not? So we want to find how strong the electric field is at a point. Okay, so at a point in the field, we want to see how strong the field is. So we have to use a positive test charge to test the field. So we put a positive test charge here, for example, a proton, and then we look at the force acting on the proton. So let's say the value is F. Okay, and the charge of the proton is Q. So therefore, the field strength of the lithium ion at this point is equals to the force on the proton divided by the charge on the proton. So that gives you how strong the field of the lithium is. That's how we define it. So some people say, why do we do this way? Because you see, do you agree that the stronger the field, the stronger the force acting on any test charge that you place there? Correct enough. For example, we look at gravitational field. So the Earth has a gravitational field, but we have also learned that the Moon has a weaker gravitational field. So when we stand on the Earth, we will feel a bigger weight. When we go to the Moon, we feel a smaller weight, right? So that's the force. So the force depends on how strong the field is. So this is electric field, which is the same concept. So your electric field has different strengths. So you want to see how strong it is, you take the force acting on the test charge and you divide by the magnitude of the test charge. That's how strong it is. Example, now let's say we use 1 coulomb charge. Let's say you want to find the field strength at this point. So we use a 1 coulomb test charge here. And the force that you get, let's say, is 2 newtons. So therefore, the field strength at this point will be 2 divided by 1. You understand that? But let's say I remove this positive test charge and I put another test charge at the same point, but it's different magnitude. Let's say it's 2 coulomb now. So will it experience the same force? Can the different charge experience the same force? No, right now. For example, we are all in the Earth's gravitational field, but we have all different masses right now. So do we all have the same gravitational force, which is our weight? No, right now. We have different values right now. So similarly, different charges will experience different force. Like in this case here, it will experience 4 newtons instead. But what is the field strength? So we calculate 4 divided by 2, which is the same as 2 right now. So why is it the same? Because the field strength at this point, of course, must be the same, because the field is due to the lithium ion one. So field strength at this point is constant, but the force experienced by different charges, of course, will be different now. You understand that? So we have to remember how to use this formula. You must take the force acting on the test charge, divide by the magnitude of the test charge, not the charge that produces a field. That means you must divide by the charge of the proton and not the charge of the lithium. Do you understand that? Okay, so the unit for field strength will therefore be newtons per coulomb. Okay, now field strength is a vector quantity, so it has a direction, which is why they define the field strength as the force per unit positive charge, because there's a direction involved. So what is the direction of the field strength? Because it's a vector quantity. Now the good news is it follows the same sign convention as how you determine the direction of the electric field, which is following the force on a positive test charge. So in other words, the direction of the field strength, let's say at this point, if I put a positive test charge, this 2 coulomb is positive, and the force is to the right, so therefore the field strength at this point is also to the right. So it must follow the same direction as the force acting on a positive test charge. That's why the definition of field strength is force per unit positive charge, to remind you that it is a vector quantity and it follows the direction of the force on a positive test charge. Do you understand? Okay? So next we are going to learn the formula for field strength between charged parallel plates. So this is an example of charged parallel plates, and remember we said that the field between them must be uniform. So if they are uniform fields, then how do we calculate the field strength? Now, no doubt you can still use the formula E equals to F divided by Q. So that is the definition for field strength, which you can use for either uniform fields or non-uniform fields. Any type of electric field, you can use this formula. But for uniform fields between charged parallel plates, there's another formula, which is E equals to V divided by D. So what does the V represent? It represents the PD between the plates. So if I apply, that means if I apply a PD between the plates as V, so how do I apply this PD? I connect it to a cell of, let's say, PDV. So then this also will have V right now across it. So the field strength between these two plates will be proportional to the PD you apply. Does it make sense or not? If the higher voltage I use between the plates, the stronger the field is. Correct? And another one, it is inversely proportional to the separation of the plates. So the closer the plates are, the stronger it is, but the further apart, the weaker it is. Does it make sense? So for your AS, you only have to remember this formula. In A2, we will actually derive this formula for you. But for AS, you just use common sense. Oh yeah, well, correct. Well, the field strength between the plates is proportional to PD, but inversely proportional separation. That's all. Okay? Now, when you use this formula, you will end up with what unit? Volt per meter. But earlier on, when we use F divided by Q, we got Newton per coulomb. So how come they have different units even though they are the same quantity? Now, actually, it looks like they have different units, but if you were to break this unit down to the base SI unit, and you break this down to the base SI unit, you will get exactly the same base SI units. So which means to say, you can leave your answer, the units as either Newton per coulomb or volt per meter. Understand? It doesn't matter. So when do I use this formula? You use this formula for any type of field, but provided you know the force lah. But whenever you see uniform field between charged parallel plates, you should try using this first, because this is easier. And furthermore, this formula can only be used for uniform field. Never ever use this formula for any other type of field. It is wrong. It's only for uniform fields. Okay? So now, another thing that students ask me, if I see, because in paper 2 you always have the answer, the space for the answer, so they put there E equals to ... then they put there Newton per coulomb. Does it mean that I have to use this formula to solve? Or if they give me the final one, E equals to ... volt per meter. So does it mean I have to use V over D? No, it's just a trick. The units they write down for you can be volt per meter, but you maybe have to use F over Q to solve. Or they can write Newton per coulomb, but you need to use V over D to solve. So don't assume that the units tell you what formula to use. It doesn't matter, because they're the same base units. Do you understand? Okay? So what do we use these two formulas for, the F over Q and V over D? Now, from the formula E equals to F over Q, we can get our formula F equals to EQ, which is the only formula that gives you electric force. So every time you're supposed to find electric force, you take the field strength times the charge. But the good news is, if it is a uniform field, the E we can substitute with V over D. So therefore, you can get the electric force this way. Okay.